Can you see my screen?
That's right. We can see your screen.
All right. I think there is some sound coming from. Okay. Thank you to the organizers for giving me this chance. My name is Moges, and I'm a PhD student at UCT South Africa under the supervision of Professor Kokos. My PhD project focuses on numerical investigation of the influence of chaos on dynamical properties of Hamiltonian models. But right now, I will present a work we published with our collaborator in France, Assistant Professor Manos. It's not easy to talk about GALI or SALI after Professor Buntis and Sakokos, but I'll try my best. On the behavior of the generalized alignment index method for regular motion in multidimensional systems. I will first start by describing the model we are using, and then the general alignment index method, which is an efficient technique as Prof described it earlier, to discriminate between regular and chaotic behavior in high-dimensional systems. It has been observed that multi-dimensional Hamiltonian models, the constant value of GALIs for regular orbits decreases and the order of the index increases. So in this work, we set out to numerically investigate the behavior of GALIs in the neighborhood of simple correct periodic orbits called SPOs of this FPU lattice. In particular, we extensively studied how the value of GALIs depend on the width of the island, which I will gonna define later, and the system's energy. So let me start with the FPU problem. It is the apparent paradox in chaos theory that many complicated inner physical systems exhibited almost exactly periodic behavior. It's traditionally called the alpha-beta FPU-T model, starting from the physical system of particles with equal masses and certain interaction here, as you can see. Here, X is the relative, this extra relative displacement with respect to the equilibrium position of the N particles. The boundary is fixed here. We are considering the beta version of FPU, which represents a one-dimensional chain of N identical particles with nearest neighbor interactions is given by this equation, where Xj is the displacement of the J's particle from the equilibrium position, and Pj is the corresponding conjugate momenta. In our study, we imposed fixed boundary conditions. We also chose to work on the beta FPU system because it is uneven degree and it doesn't allow the particles to escape. Then the corresponding equation of motion for the Hamiltonian functions will be given by these two equations. And these two sets of differential equations can easily be integrated. By the way, in our study, we set beta to be 1, and we rather use the energy and what we call the size of stability island as a controlling parameter instead of beta. Okay, so these are the SPOs we study, which are which can be found in Professor Buntis' paper. SPO1 and SPO2. The first one, SPO1, is obtained by considering this the beta FPUT system with n being an odd integer. that all particles at even number positions are kept stationary, and the odd number particles are always displaced symmetrically in an opposite direction. If we consider, for instance, n equal to 7, the odd numbers, as you can see, the first one, the third one, and the fifth one, sorry, the first one, the third one, the fifth, and the seventh one are equally displaced and in the opposite direction, plus minus, whereas the second, the fourth, and the sixth in kind of greenish color are fixed or 0. And if we consider the SpO2, which is the one here, in this case, particles correspond to arrangement where every third particle, 1, 2, 3, are stationary, whereas the two particles in between move in the opposite direction. So if we consider n equal to 8, as you can see similarly, we have this, the third and sixth are 0, and the first, the second, and the fourth, fifth are in the opposite direction, and they are symmetric. I think you get the idea. So in general, mathematically, the SP1 is for n degrees of freedom is given by this equation, and apply using this condition, we can have a second order nonlinear differential equation, as you can see here. Okay, so in general, SPO1, in general, regular motion occurs in the vicinity of stable periodic orbits in Hamiltonian system. Thus, in order to study the behavior of GALIs for regular orbits, we first locate some stable periodic orbits of our system, and then we compute the GALI for orbits in the neighborhood of these orbits. Stability type is, we determine the stability type by the eigenvalues of the so-called monodromy matrix. This matrix is obtained from the solution of variational equations of periodic orbits for one period t. Further can be found in this reference. Now, if all the eigenvalues of this monodromy matrix are on the unit circle, in the complex plane, the corresponding periodic orbit will be stable. Otherwise, we will have unstable periodic orbits. To illustrate, we can see this plot, the arrangement of the eigenvalues of the monodromy matrix of SPO1 orbit in the FPUT beta system with 11 particles. As you can see here, we have 0.1 energy per particle, and here it is 0.2. In the left, the SP1 is clearly stable since all of the eigenvalues are in the unit circle, whereas in the right it is unstable because all of them are not in the unit circle, or in particular these two are on the red are of the unit circle. Okay. In general, initial conditions close to these stable periodic orbits leads to regular motion, whereas the initial conditions which lie in the vicinity of these unstable periodic orbits, in this case, chaos appears. The stability analysis of SP1 shows that for small values of energy per particle, the orbit is stable. And it becomes unstable when the energy increases a certain threshold, and the threshold for SPO1 for n equal to 11 is around this value. And the authors in this paper computed the energy density threshold for different number of particles, and they showed that the energy per particle, it decreases as the value of the the value of the particles, the number of particles increases following this power law. As you can see here, the reciprocal of the number of particles. The energy per density of the first stabilization threshold of SP1 for this, in this case, beta, as I said, we said beta equal to 1. And this straight line is, it corresponds to the function that follows this asymptotic law. Okay, so the generalized alignment index, as I said, Prof. Skokos already explained it very well and gave you good examples. So I'm not going to go through it in detail. However, I will briefly discuss how we are computing it and give the results we found in our work. In order to compute the GALI chaos indicator for a particular orbit, we have to follow the evolution of orbits, along with initially linearly independent deviation using along with perturbed orbit, or this deviation vector. The time evolution of the initial vectors, or the so-called the variational equation, is given here. Already explained earlier, so let me just skip it. And let us now briefly discuss the GALI method, its property, considering our n degrees of freedom autonomous Hamiltonian. The generalized alignment index of order k represents at any time the volume of the generalized parallelogram having as h the k unit deviation vectors. The volume is computed, as you can see, the norm of the wedge product of these k vectors. The GALI is a generalization of the so-called the smaller alignment index, or SALI, and GALI2 is practically equivalent to SALI, and both indices have been proved to be very efficient chaos indicators and have successfully used, for instance, you can see, check out this paper. Okay, so how are we computing this GALI? An efficient way of computing the value of GALIs is through the singular value decomposition technique. The singular value decomposition of this matrix, where this matrix is having as columns the coordinates of the k unit deviation vectors. In particular, GALI k is the product of the k so-called singular values of the transpose of A, obtained through the singular value decomposition procedure. Our main focus is the behavior of GALIs for regular orbits, so we are not interested in the chaotic case here. However, let me quickly just say something about its chaotic behavior. For chaotic orbits and also unstable periodic orbits, GALI k decays exponentially fast to 0. In case of chaotic orbits, GALI k decays exponentially, in case of chaotic orbits, the two, for instance, if we consider only two particles, the two deviation vectors tend to coincide in the direction defined by the two largest Lyapunov exponents. You can see it, the relation in the figure here. This is GALI towards SALI with respect to time, and as you can see, it goes to 0 quickly following this relation described here. Okay, so GALI for regular orbits. In an n degrees of Hamiltonian system, the system's dynamics leads any deviation vector of the regular orbit to eventually fall on the n-dimensional tangent space of the torus. Thus, asymptotically, the volume defined by k linearly independent deviation vectors from 2 to n will not become 0, as the vectors will remain linearly independent, so it will be constant or positive value, while these vectors will become linearly dependent, in which the volume becomes zero following this relation between n and to n. If you are wondering what will happen if the number of deviation vector k exceeds the dimension 2n of the system of the phase space, in that case, as previously mentioned by the previous presenter, the definition tells us the vectors will be linearly dependent and the corresponding volume will be zero. Let's consider a particular case here, a regular orbit that lies in a 5-dimensional torus. In the figure, you can see the time evolution of the normalized GALI indices from 2 up to 10 for a regular orbit. So for regular orbits in a 5D torus, from GALI 2 to GALI 5, eventually oscillates around non-zero constant values, which decreases with increasing k from 2, 3 up to 5. While GALI k go to 0 following the asymptotic law after 6 with up to 10, which means 2 times 5 are degrees of freedom.
Please unmute yourself. We cannot hear you.
Deviation vectors. That means if we take different random choice of initial vectors, it fits us to a different GALI value. So to statistically analyze the behavior of GALI, we decided to take several sets of initial deviation vectors and take an average. Okay. So to investigate how GALI behaves for regular orbits, we perturb the stable SPO1, x I hat, p j hat, getting a nearby distance, which is this capital X and P, by keeping the total energy fixed. Then we determine the phase space distance, which we call D, using this Euclidean norm. We follow the evolution of this normalized GALI and corresponding average values for 10 sets of random deviation vectors. And the average GALI over 10 sets is given here. And the estimation of the asymptotic GALI value or average GALI value at the end of each integration time. GALI 3 is this one, and GALI 3 is this one, and GALI 11 is around here. Here, the error bar represents one standard deviation, which is computed through the standard deviation of the averaging process. Now let us investigate how this behavior changes when the studied regular orbit is taken further away from the stable SPOs. To do that, we use different D values here, or from D1 up to D6, as you can see here. D1 being close to the SPO1, while D6 is further from the stable periodic orbit. Here we are computing GALIs using a single set of random initial deviation vector. First of all, we observe that the behavior of the GALI for regular orbits closest to the SPO1, which is D1. It followed the same power law as the periodic orbit itself, which is to the power of -1. And here it is GALI 4, so it is to the power of -3. Sorry. GALIs, so as we increase GALIs, it starts moving from power law decay, and finally they become constant. As you can see, D2, D3 up to D5, the same is true here. And in time, for large values of D, as you can see, D6 in both cases, the perturbed orbit becomes chaotic since it will be outside the stability island. So the GALIs decrease exponentially fast because it's chaos. Okay, so now we can see the values of this estimated GALI as a function of K for regular orbits in the neighborhood of stable SP1 for increasing D in this case and for increasing energy per particle here. If we see the one on the left, note that the values of GALIs for regular orbits, it grows with increasing distance D. D1 being the red one and D4 the blue one. So we see that this estimated GALI K increases with respect to D when we go from D1 is around 0.1 and D4 is around 2.2. There is also another way to move from stability to instability. Instead of increasing the D, if we increase the energy, we will go to instability. That's by increasing the energy densities instead of the size of the stable island. Of course, we have to keep the energy below the destabilization energy SPO1, where the periodic orbit is stable. So for this case, the asymptotic value of GALI, the smaller one is, as you can see, the red one, and the blue one is the larger energy value. So GALI decreases when we increase the energy. So we try to estimate the extent here in order to see how GALI values change when we increase the order's energy density. We begin by estimating the size of the stability island around SPO1 orbit with different energy per particle by finding the largest D value for which the regular motion is observed. So the size of the stability island decreases as we increase as the energy grows and vanishes when we reach the destabilization energy. If you remember, it was around 0.176 here. Thus, the region below this curve corresponds to regular motion. So the figures we have so far, or the results we have so far, they are not restricted to SPO1, but are rather more general. So to demonstrate this, we did the same analysis for SPO2. This periodic orbit SPO2 appears where every third particle, as you can see here, remains always, sorry, every third particle remains stationary, and the two particles in between move in the opposite direction. So a similar analysis is performed for regular orbits, and the findings of SC1 remains the same. When we increase D values, again, GALI is increasing, but when we increase the energy, the GALI value is decreasing. To make our analysis more complete, we did similar analysis for different value of particles. Here, as you can see, the result for larger values of N are presented. And we can see also the same monotonic relations as observed for 11 particles for values of D here and for values of E here. There we can say that our findings are clearly independent of the type of SPOs, because we use two SPOs, and the value of N. Another very important finding is that the evolution of GALIs it doesn't depend on the initial choice of deviation vectors needed for their computation. To illustrate this property, we consider different sets of initial deviation vectors whose coordinates are drawn from different type of probability distributions, and we computed the corresponding GALI values. Here, what we did was we consider a uniform distribution on the first panel here, and again we computed GALI for instead of uniform. First, we are orthonormalizing the deviation vectors. That means basically taking the maximum GALI value, which is 1. And we did both analysis, and as you can see, what we again did was we used different distributions. We used normal distribution and uniform distribution. And both curves, as you can see, they overlap. To the distribution created, we also checked the probability density distribution of the coordinates, only taking GALI 11, which will be 11 initial units or orthonormalized deviation vectors. And as you can see, they also overlap. So in both panels, the two curves practically overlap. So to summarize, the values of GALI K eventually saturates to positive values for regular motion on an n-dimensional torus. The asymptotic GALI values depend on, firstly, the order of GALI index. That is, GALIs of higher order attains smaller values. It also depends on the phase space distance d of the regular orbit from the nearby SPO. And we said that when GALI values increases when we get closer to the edge of the stability island. And it also depends on the orbit's energy. As we approach to the destabilization energy of the SPO, the GALI values decreases. And GALIs are independent of the initial distribution of the coordinate of the deviation vectors. Finally, I would like to thank the UCT Science Faculty PhD Fellowship and UCT International Scholarship. Thank you very much.
Okay, thank you to the speaker. Thank you for such a detailed talk. Any questions or comments? Okay, there are no questions or comments, so the
okay.
is over. Thanks very much.
Thank you.
And see you all tomorrow.